Alright folks, welcome back to the channel. Today, we're diving deep into a topic that's at the heart of every computer CPUs and GPUs. You've heard these terms thrown around, especially if you're into PC building or gaming. Central Processing Units or CPUs and Graphics Processing Units or GPUs. They sound similar and they both process stuff, right? Well yes, but they do it in vastly different ways. Think of them as the ultimate tag team, each with its own special moves. The CPU is the workshop manager, making all the big decisions and handling complex instructions. It's the brain, the general, the one calling the shots for almost everything your computer does. Now, enter the GPU. If the CPU is the workshop manager, the GPU is like an army of highly specialized workers. Originally, these workers were all about one thing, drawing pictures on your screen. That's why it's called a graphics processing unit. They were designed to handle the thousands, even millions of calculations needed to render beautiful, smooth graphics. GPUs have become so powerful at these parallel tasks that they're now used for way more than just pretty pictures. We're talking scientific research, artificial intelligence, video editing, and a whole lot more. Stick around, because we're about to break it all down. Let's talk more about the Central Processing Unit, or CPU. This thing is the brain of your entire computer operation. Every time you click your mouse, type on your keyboard, launch an application, or even just move your cursor, the CPU is involved. It's the primary component responsible for interpreting and executing most of the commands from your computer's hardware and software. Think of the CPU as an incredibly skilled orchestra conductor. The CPU manages all the different parts of your computer, your RAM, your storage drives, your peripherals, and yes, even the GPU. It fetches instructions from memory, decodes them, and then executes those instructions. This cycle happens billions of times per second. It's a true multitasking maestro. The CPU is designed for general-purpose computing, handling a wide variety of tasks quickly and efficiently. When you open a new program and it pops up almost instantly, that's your CPU working its magic. So yeah, the CPU is a pretty big deal, the unsung hero of your digital life. So how does this brain actually process information? It's not magic. At its core, a CPU operates on a fundamental cycle: fetch, decode, and execute. First, the CPU fetches an instruction from your computer's memory, RAM. This instruction is basically a command telling the CPU what to do next. Once the instruction is fetched, the CPU moves to the decode stage. Here it figures out what that instruction actually means. The CPU has a special part called the instruction decoder that translates this binary code into actions the CPU can understand and perform. After decoding, it's time for the execute stage. This is where the CPU actually performs the operation. It might involve doing an arithmetic calculation, a logical operation, or moving data from one place to another. This entire fetch, decode, execute cycle happens incredibly fast, billions of times per second, measured in gigahertz, GHz. Modern CPUs also have multiple cores, allowing them to handle multiple tasks simultaneously. Higher clock speeds and more cores usually mean a faster, more powerful CPU. Now let's shift gears and talk about the Graphics Processing Unit, or GPU. The GPU's main task was to take data from the CPU and turn it into the images you see on your screen. To handle this monumental task, GPUs are designed very differently from CPUs. A GPU has hundreds or even thousands of much simpler, smaller cores. This architecture is perfect for tasks that can be broken down into many small, identical, independent pieces, a concept called parallel processing. Because of this incredible parallel processing capability, GPUs are now used for more than just games. The humble graphics card has evolved into a computational powerhouse, driving innovation in fields far beyond just visual entertainment. Section 5, CPU versus GPU, the Big Performance Smackdown. So we have the CPU, the versatile brain, and the GPU, the parallel processing beast. How do they stack up in performance? It's not a simple case of one being faster. CPUs excel at low latency tasks. Latency is the delay before a task starts. CPUs switch quickly between complex tasks. This ensures system responsiveness. GPUs handle massively parallel tasks. Throughput is the total work done in time. GPUs might have higher latency for single tasks, but excel in parallel processing. Think about shading all the pixels on a screen. Each pixel calculation is simple, but there are millions. GPUs with thousands of cores handle these calculations simultaneously. CPUs are for complex tasks, GPUs for simple parallel ones. Neither is better. They are optimized for different workloads. Section 6. Why your CPU is still the undisputed champ for some things. Despite the incredible rise of GPU computing, your CPU is still absolutely essential and in many ways the undisputed champion of your computer. You simply cannot build a functional computer without a CPU. It's the component that runs your operating system, whether it's Windows, macOS, or Linux. It handles all the fundamental tasks that make your computer, well, a computer. One of the CPU's biggest advantages is its versatility. It's designed to be a jack of all trades, capable of handling an incredibly diverse range of tasks. Modern CPUs have instruction sets that are far more complex and comprehensive than those found in GPUs. This allows them to execute a wide variety of program types efficiently. Another key strength of the CPU is its low latency performance. This is critical for interactive applications where you expect an immediate response to your input. Many tasks are inherently serial or don't parallelize well. For these kinds of workloads, the high clock speeds and sophisticated architecture of individual CPU cores are far more effective. Section 7. GPU glory unleashing the power of parallelism. The GPU's main claim to fame is its absolutely mind-blowing capability for parallel processing. Having thousands of cores working together in unison allows GPUs to achieve computational throughput that CPUs can only dream of for certain types of problems. The most obvious application, and the one GPUs were born for, is graphics rendering. Every stunning visual in modern video games, every complex 3D model in an animation, every special effect in a blockbuster movie, these are all brought to life by the sheer power of GPUs. Beyond gaming and visuals, the parallel architecture of GPUs has unlocked new frontiers in scientific computing and artificial intelligence. Complex simulations in fields like physics, chemistry, and meteorology often involve performing the same calculations on massive datasets. In the world of AI and machine learning, training deep neural networks requires processing huge amounts of data and performing billions of matrix multiplications, a task perfectly suited to the GPU's parallel nature. This has fueled the AI boom we're currently experiencing. Section 8. Picking your player, CPU or GPU for different tasks. So, when it comes down to it, which processor should you prioritize for different tasks? It's not always a clear-cut either-or situation, as many modern applications are designed to leverage both the CPU and the GPU. For example, let's talk about gaming, a field where both are absolutely critical. Your CPU handles the game's logic, artificial intelligence of non-player characters, physics calculations, and managing your inputs. Then for gaming, your GPU takes over the visual heavy lifting. A more powerful GPU will allow you to play at higher resolutions, enable more demanding graphical settings like ray tracing, and achieve higher frame rates for a smoother, more immersive experience. What about content creation, like video editing or 3D rendering? Here too, both play important roles, but the GPU often takes center stage for specific, intensive parts of the workflow. For general everyday computing, browsing the web, sending emails, working on documents, watching videos online, your CPU is doing most of the work. For artificial intelligence and machine learning, particularly the training phase of large models, GPUs are almost always the preferred choice due to their parallel processing power. However, for AI inference, running an already trained model, CPUs or even specialized AI accelerators can sometimes be more efficient. It truly depends on the specific workload. Section 9, the final verdict. Who wins the ultimate showdown? So after all this discussion, who is the ultimate winner in the CPU versus GPU showdown? Well, if you were expecting a simple answer like the CPU is better or the GPU reigns supreme, I'm afraid it's not that straightforward. The truth is, there's no single winner because they aren't really direct competitors for the same job title. The CPU is the indispensable brain of your computer. It's the versatile, quick-thinking manager that handles the operating system, general applications, and complex, sequential tasks that require low latency and intricate logic. The GPU, on the other hand, is the specialized powerhouse, the master of massive parallel processing. When a task can be broken down into thousands of smaller, similar pieces, the GPU steps in, and delivers a level of throughput that CPUs simply can't match. Ultimately, the better processor depends entirely on what you're trying to do. For everyday tasks and overall system control, the CPU is paramount. For breathtaking graphics and cutting-edge AI research, the GPU is indispensable. So the real winner, it's you, the user, who gets to benefit from the incredible capabilities of both these amazing pieces of technology working in harmony. Thanks for tuning in, and I'll catch you in the next one.